Hey everybody! So we are looking at ionic bonding today, and by the end of this lesson you should be able to compare qualitatively, which means by comparison, the relative strengths of ionic, covalent, and metallic bonds, and infer the type of bonds and chemical formulas formed between atoms. So for this, we're really focusing on just ionic today. And before we get started, you may want to review cations, anions, dot structures, and the octet rule. So ionic bonding, we're going to jump right into this. Remember that all atoms want 8 valence electrons. So we want 8 electrons on the outer shell. We want to look stable like a noble gas. And this means to do that, we will transfer electrons from metals to nonmetals because we'll get rid of our valence electrons on the metals and go down to 8 on our inner shell. And then the nonmetals will fill up their outer shell with 8 or 2 8. And this also means we'll move them from cation to anion. So for ionic bonding, I could refer to these either way, metal to nonmetal or cation to anion. You need to know both. And we need to see that in an ionic compound where bonding takes place, we have a net charge of 0. So that means if we have a metal that lost 2 electrons, we need to have nonmetals that gained those 2 electrons. So they need to cancel out. To balance these charges, you can use as many of each element as you need. So let's say we have a metal that loses 2 electrons, but it's partnered with a nonmetal that only gains 1 electron. That means you can use 2 of those nonmetals to transfer those electrons over. Ions will combine in the simplest whole number ratio, so least common multiple, lowest ratio that we can. That's referred to as a formula unit. And then the dot structures for your ionic compounds look like ion dot structures. Okay, so we're going to follow that last bit from the Lewis dot structures video. So here's an example. So if we wanted to partner up calcium and chlorine, we know that calcium has 2 valence electrons that it wants to get rid of. Chlorine has 7, so it only needs 1, which means we're going to have to use 2 different chlorines. So one of them will go here from the calcium, will go to 1 chlorine. Well, calcium still has 1 extra electron it needs to get rid of, so it's going to go to another chlorine and partner up. And then once you transfer those electrons over, you would write this with their dot structures as such. Like you don't have to use X's and O's here to show the difference. You could just write the regular dot structure. So now let's go ahead and do our dot structures for Na and Cl, which you can see here, but I'm going to go through the steps. So you write the individual dot structures for each, and then you determine the charge, and you move the electron from one to the other, from the cation to the anion. And then you'll draw the dot structures for each ion in that bond. So we have our dots, regular dot structures for Na and Cl. We're going to, move that electron from Na to Cl. And once you do that, you will write them as their ionic structure form. Okay, and then based on the charges of your ions, make the complete compound have a charge of 0. Now, I want you to pause the video and try to do this for magnesium and bromine. So let's quickly go over ionic compounds. So first off, biggest thing, we know that ionic compounds have ionic bonds. And ionic bonds are the electrostatic force that hold these ions together. And it forms exactly the way we just talked about. You will transfer electrons first, form your ions, then they will bond together. So they don't form the bond to transfer the electrons. They form the bond because they transferred electrons. So you have to move the electrons first, then the ionic bond will form. Once that has formed into an ionic compound, they have very specific properties as well. First being super high melting and boiling points. So that means they have a very, very strong bond. As reference, with a Bunsen burner in the lab, we cannot get hot enough to melt most ionic compounds. Okay, it's got to be extremely hot. These conduct electricity, but only when they're molten, which means melted, or dissolved in water. So anytime we say something is dissolved in water, it's described as aqueous. So that's the definition. So you can't plug up an electrode to a pile of salt and it conduct electricity, but you dissolve that in water and then put the electrons in, and it will conduct electricity. These will be in crystalline solid form at room temperature. So if you've ever looked at a salt crystal, it's very geometric. It's not like any random shape. It's very cubical, and that's due to this crystalline solid property. And that also means that if you apply a force and break the ionic compound, it will break at the angles that you see in the crystalline solid. It won't just shatter or anything. These are usually non-volatile, which means they don't go into gaseous state easy. Normally means they don't have much of a smell. You'll still have some smell, but not a strong odor. And then ionic compounds can also form through what are called amorphous solids. And this is a solid that has no internal structure. So we'll see this sometimes with ionics. You'll see it a lot with like covalent compounds, organic materials. But they have no internal structure, which means if you break them, they will shatter at whatever shape they want to. Think glass, rubber, things like that. Plastic. That's why like plastic water bottles can be all different shapes and sizes, because plastic does not have a rigid structure.